Okay guys, this one here is AE2. So AE2 is analysis and evaluation 2. Analysis. Okay, so it's another one of these where we're actually analysing what has happened in the experiment, and we're also evaluating our procedures specifically. So in this case here, you're expected to, at an A level, critically and logically evaluate procedures and suggest, doesn't say, in depth and all that sort of thing, a range of appropriate improvements. So if we are critical and logical, so critical, once again, what you are doing is forming some sort of evidence-based argument. Okay, so what evidence is there for those types of errors, or for any errors whatsoever? So if there's some sort of appropriate improvements, there's got to be something going on that's not quite right. So we've got two types of error: random, systematic. We make a judgment on how significant the error is. So high, moderate, low error. High precision would mean low random error. High accuracy would mean low systematic error. So we make some sort of judgment, and then we support that judgment. It actually doesn't really matter whether your judgment is kind of right or not, because it's all subjective. So your judgment on low random error might be you might say, oh, no, there's low random error. I might think there's actually quite a lot. So as long as you make some sort of judgment and are then able to support that judgment with evidence from the data that you've collected. So let's say we have some sort of graph. That's our line of best fit, and those are our scattered points. You can see that low random error, high precision, evidence being that there's not much scatter in the graph. It might mean that, let me get a different colour, it might mean that you had a graph that went through here, and similarly those are your data points. Same sort of deal, so low random error, high precision, once again not much scatter in the graph, but the y-intercept is really big, and most of our data graphs, the equations, especially when we're dealing with circular motion, we ended up with this sort of relationship. There's no y offset, there's no y equals mx plus c, there's no plus c here. All we've got is v squared is mgr over the other m. So you end up with some sort of relationship, and you might have been changing the radius, so your m, I guess the slope is actually that part there in the brackets. There's an r, that's your x term. V squared is on the y-axis, that's the y part. But there's no plus c, that doesn't exist. So it should go through the origin. It won't all the time. All right, that would be evidence of systematic error. So random error is the method that you've actually chosen. So when you're suggesting a range of appropriate improvements, the improvements are to the method that you've used. So if there's low random error, the changes to the method aren't going to be significant. If there's low systematic error, the changes to the equipment aren't going to be significant. Okay, so this is to do with you, this is to do with the equipment. Okay. So when you're critical, you're actually using evidence to support your argument. When you are logical, you are following some sort of pattern in the way you're analysing it. So it wouldn't be low precision, high systematic error, and then just start randomly assigning different parts of your method or the equipment to one or the other. You're following some sort of pattern. Okay, this section here is going to be just systematic error, then there's going to be just random error. Okay, so you're following some sort of pattern. It is also supported by something like this. So your mistakes, your evaluation of your procedures, you are not finding really stupid ways to improve it, I guess. So it's how can I put it? If the procedures are logically evaluated, what you're looking for is things that are realistic. Let's put it that way. So it might be, you're timing the revolutions in this experiment for 10 times. We might say, oh, let's do it for 100 because that'll reduce the impact of random error. Well, okay, is there much random error? Will that 100 revolutions actually do that much to your data? No, it won't. So why would you bother doing it? It's not realistic to do that sort of thing. Alright, so when you're suggesting a range of appropriate improvements, appropriate ones that are still the same thing, they are still realistic or doable, it's something that you actually have access to. So you've got access to the equipment, so you're not talking about laser fields and CGI tracking and all this sort of weird stuff. It's what can you realistically be expected to do in a reasonably well equipped stage 2 physics lab. Yeah, so is it realistic or doable? Do you have access to that type of equipment, and will it really improve what you've done? If the answer is no, again, why bother? It's not appropriate improvement that way. Appropriate improvements will also so if you've said that the systematic error is caused by significant amount of friction between the fishing line and the inside of the tube, again in this experiment here, then what could you do to minimize that source of error? That would be appropriate. Alright, suggesting a range of improvements that actually don't fix any of these things up here, once again, that's not really appropriate, is it? So this is AE2 again. AE1, AE2 and I1 are the heart and soul of the scientific method. So these are the ones that are generally looked at first, or they're the ones that I look at first when I'm doing moderation. If someone said it's fantastic work and these ones here aren't, then it doesn't deserve a fantastic grade. Okay. Look for these types of videos coming throughout the year, especially when you guys are doing pracs. Refer back to them as often as you like. I will leave them on public, so you can go to there. I should have just said this instead of writing it down. Stage 2 physics, and then I think it's flipped videos or something. You'll find them. Anyway, feel free to drag and drop them onto your own desktop, take them home. They're also obviously on YouTube. Cheers guys, we'll see you next time.